that integration is basically necessary. That is developed by those who develop quantum computers and those who work on the algorithmic side, that is quantum ML, so that both understand the requirements and the nuances of each other, and through that basically something contributed. Again, the other point that is while this project between Marseille and National Institute of Silchar actually was submitted and then took place, I was at the institute as the director of the institute, and being a PhD, obviously we identified myself and Prof that quantum NLP is going to be the one for the path for the future. So why not submit a project proposal? And so before I left the institute, so the project was sanctioned, and you can see the result. And obviously, that is with all the difficulties in my left ankle at this moment. So I prefer to come here to see that there is a seed that we have shown at NIT Silchar, so that has been the interactions or the growing interactions between the two institutions for the future. So some bit of NLP, but not the details that what Alexis was giving in the morning, because my job is to find out where lies the importance of quantum NLP, or why people like us are actually feeling that quantum computing has to be brought into the system. One is that so if you understand that is, and maybe many of you actually know that is quantum with the context-free grammar. Yeah. With the context-free grammar by Noam Chomsky. So the seed for the formal linguistics started, and from that basically there came the symbolic approach. So when we started our work in say 1985 or so, so we worked on the symbolic approach basically, and as a language, when we learn language in our school days, the focus becomes on the syntactic structure basically. But as time grows, and everyone knows that when people have started writing in the social media, so the grammar rules are actually broken. So people have started writing things on their own. So that is the situation. So initially, the machine translation work was the main application of NLP. But in 1964, when the ALPAC report basically came out with the conclusion that rule-based approach to machine translation will not work any further, so many of the research activities on machine translation that basically came to a stop. Then in the 90s, so NLP shifted from a rule-driven technology to a data-driven one. And from that point onwards, it has actually not looked back, more towards data, a large amount of data. And the language modeling that we basically talk about, the large language model that has come into place nowadays, and what everyone identifies or any further syntax or anything. So more data and more language data will actually solve the purpose. But there are people, maybe senior people like us, who think that LLM is not the solution always. So hallucination is basically one of the areas of LLM that is which needs to be taken care of. So when the data-driven approach basically started, initially it was a statistical NLP, that is because the data was not of that high scale. And IBM's alignment model came into being. Even during that period, the factored statistical machine translation, so people developed, Philip Cohen worked on that part, and that was basically keeping syntax into the data-driven approach as well. But when more and more data came, so obviously the syntax basically went into the background. But the problems that came at the same time, that is why we concentrating on the syntax part of the, I should say the structural part of the sentences, is basically that if you consider everything, all the data as a bag of words, explainability or interpretability of the output of a
system becomes a question. But interpretability, because otherwise everything looks like a black box. For example, say in the deep neural network structure, people you give the data, and it identifies the features itself, gets you a solution, and you do not know how to tackle that is if there are some gaps here and there. So how to look into that part? So interpretability or explainability, that become a problem. So then the neural networks basically came into being. One is that was one way of doing the work, architectural side. The graphics GPUs or the graphics processing unit and the cloud computing, that became necessary because more and more volume of data was being generated, and so and the result has to be given in the quickest possible time. And in the neural network, you have the feed forward model, that is run the network to find an answer, or you go into the back propagation model, basically train the system to improve on the weights, and that is the different parameters, and then finally find a solution to it. So that actually, that is earlier the rule based approach we termed as a symbolic approach. Now it is a connectionist approach. That is the low level structure of the brain. The connectionist approach was basically looking into, that is individual neurons, they are working on their own job, and the interconnections between them, the architecture of the neural network, that becomes important. And neural networks become the state of the structure for many a time. Now, next came the deep neural network. Again, the progress was basically computational power, and with large volume of data that are being generated. So you need to have more and more layers in the neural network. So that is the basic thing. And various fields which have been applied, but they were showing effective performance. But along with that came the issue, like say the complexity in the model, excessive data set, because otherwise, say for low resource languages, getting computational model or a system became very difficult. So that kind of research in the low level language, people are actually looking whether collection of data is the only solution, or working with the structure of the data that becomes a solution. So in power, computational power, time, and the resources. So at this point, actually, the thought for using the quantum computing that came into play. So one issue was basically the structural part. That is what, with the language processing, what was missing is the structural part of the sentences, and through that, interpretability or explainability of the output of a system, or that cannot be answered. That was becoming a question. Second issue was basically with a large volume of data, because that has its positive advantage. So how to handle that part, because storage was becoming an urgent necessity, and individual, say the university laboratories, unless they have a good funding, they cannot store that amount of data. Processing also becomes a very issue, that is the access to GPUs and everything. So cloud was many solution for many of the situations. So then the issue of the quantum computer of in the area of energy, that basically. So obviously, fortunate that the slides related to quantum computing are not basically going through them in detail. Among the quantum computing properties, I think superposition and entanglement, these two already a lot of discussions have been done since morning. The superposition is basically important while looking at the storage issue basically, because say from the classical data to the quantum data, if the encoding basically reduces the size of the storage requirement, quantum requirement. So that is one thing. And entanglement, one area that I can say that becomes very important, is basically when we are trying to give a structure to a sentence, that is because we have talked about word embeddings. how the meaning of a word in an word embedding format or the what to rate format that is represented in a neural model. So similar to that, how a sentence embedding, that is how the different words that constitute a sentence that can be stored basically. There the concept of entanglement basically comes into picture. Along with superposition and entanglement, the issues of interference and the measurement issues. So those, I should say, those nuances also came into picture. Nuances, it increases the probability of the desired outcome. So probability becomes an important. So you might run your quantum algorithm and the corresponding code in a simulation system, may get very good results, but next time when you run it on a say quantum computer at the background or run the simulation again, you may not get the same desired result, because the kind of errors that can creep in into the system, and one part obviously comes from the measurement, because measurement in a quantum computing is basically, say, your quantum or qubit can be in any of the states between 0 to 1, but as soon as you do the measurement, with certain probability, it will go back to 0 or it will go back to 1 basically. So that becomes actually very important. So error becomes an important issue. So these slides skipping because you had very good detailed explanations and tutorial kind of things. Quantum measurements also, that is, it is basically a probabilistic measurement. Quantum operators, different qubit gates, that is those who work on the started from the digital domain, that is the logical and or NOT gates and etc. XOR gates. So correspondingly in the quantum domain, there are similar gates are there, and the whole philosophy or the whole science of working in the quantum mechanics is basically to the matrix manipulation. So then comes, because the machine learning approach has to be there, because with the quantum compute, because we have a large volume of data, so that means machine learning approach, because you have to find a pattern that is present within the data. And just now, Assam has given a very detailed explanation that is where you can define quantum machine learning. So it is the joining of quantum computing and the machine learning algorithms. So that is known as the quantum machine learning method. It improves the runtime. That is one thing. Second part is the learning efficiency, because pure amount of training data is necessary, and that is again because the number of parameters, tunable parameters that are there in the quantum computing, that is or the parameters are parameters or tunable parameters that are very less in number, and so obviously that makes the learning more efficient. And the storage obviously requires less, because of the way the quantum data they are actually stored in the system. That is the encoding part basically. The quantum machine learning, that is from the system point of view, basically consists of two parts. One is that because the data is generally generated in the classical format. So that is the classical data, so that has to be encoded first into the quantum model. And then when the quantum data is there, then it goes to the machine learning models basically, that is working with the quantum data. And in the QNL, they work with the variational quantum circuits basically, that is the with the help of the parameterized gates and other gates. So the encoding methods become important. There are basically three encoding methods from the classical to the quantum. One is a basis encoding. For each classical data point, there has to be a basis quantum qubit. That takes a lot of time, a lot of space basically. Then you have the amplitude encoding. So that actually for a data set, say with
n number of features. So that storage requirement is actually very less at the logarithmic scale, and you can see that that is a so if you are basically log linearly is to encode n-dimensional data with n number of samples. And so this is obviously an advantageous one. But again, the current capacity of the quantum computers in terms of qubits, they are not that high. That is what we generally have access to. So we cannot work with a large volume of data with which the deep learning networks they have stored. They are working. So all the data, detailed data that are generated or used by the deep learning models. So all of them are that large volume of data cannot be utilized. But amplitude encoding, in that case, that helps to reduce the storage requirement. Then angle encoding, because the way the qubits are actually physically conceived, that is that is from 0 to 1 on the along the three axes, the angle that it generates basically. So based on that, the value of the qubit is you can identify, and so that is the basic concept of angle encoding. But I'm not going to flood your mind with these details of equations and everything. But basically, what we can conclude at this point is that encoding becomes an important issue. That is why NLP people think that, okay, let's go for or look into or explore the quantum computing issues. And among them, the amplitude encoding and the angle encoding, these two are basically used for classical to quantum data conversion. Now, variational quantum circuits, so they basically implement the QML models. And so training means that the parameters that need to be tuned, and they are actually very less in number. And so because that tuning, so the cost function has to be defined, and it can be the finding the lowest energy state of a molecular system or optimizing the parameters of a machine learning model. Similar to the gradient descent technique used in the deep learning models, so there are quantum gradient descent techniques also to find out basically for what values of the parameters, the performance of the training file that becomes important. Now, challenges for developing a practical QML system algorithm is the high error rate of the quantum hardware. So that still is a problem. That is why that is the focus by IBM or other big shots. They are on identifying the error correcting codes, because the performance, if that has to be a real industrial solution, so the focus is on the error correcting codes basically. So ongoing research in developing error correcting codes for quantum computers, and another area is basically classical quantum machine learning approach. So hybrid approach will remain, because as we were just listening, that is after measurement from the output of the quantum system, it goes to the classical model, and then you can do your work on that part. So these hybrid approach that becomes important, and obviously practical and the scalable model, that is important. And another issue from the NLP side is basically that for low resource languages, where the volume of the data with respect to deep learning models is not that much, but as a computational linguist person, you need to provide technical solutions to all the living languages in the world. So they are also for low resource languages. That is another area of focus or research, I should say. That is where people have got the potential to work there. So some of the concepts that we need to basically look into, that is similar to the classical neural network. We have the quantum neural network also. And in classical neural network, we have say a set of inputs on the neurons, x1, 2, etc., xn.
and that gives one output that goes to the next state. And similarly, if there is a multi-layer one, so these outputs basically then they collect together, they generate a solution. So whether it is a classification problem or it is a generation problem, basically. Now, in case of quantum neural network, the data has to be represented in this way. That is the way we have said, where 0 is known as the ancilla qubit. Now, why that is necessary? Because in neural network, the result from the previous state that has to be forwarded to the next state, so that the ancilla qubits become necessary, because all other bits now, when they are measured, so they cannot with a certain probability they will either go back to 0 or go back to 1. But the ancilla qubit, that will remain. So this is the multiple qubits, x1, x2, etc., xn. Those are basically the feature values, you can say, allowing for non-demolition measurements to determine errors without altering the state of the physical qubits. And one of the challenges in developing Q neural network is the need for error correction. Different QML platforms, so I think my colleagues later on also, they'll talk about, so Amazon Bracket or Pennylen or IBM Qiskit or TensorFlow Quantum from Google, and there are other platforms also. They provide you with a simulation platform, and at the background also, you can run your quantum codes in certain quantum computers, which they basically subscribe to. Now, initially, when we started our talk, we basically talked about, that is, how the syntactic structure, because the sentence structure was missing when we went for the data-driven approach. So the DiscoCat model, that is the distributional category, and this came out in 2010 at the University of Oxford by these three people, and it combines the embedded words along the grammatical structure of a sentence to encode its meaning. And the algorithm has an exponential speed up when implemented on a quantum computer. And because as we understand, that is, the language has got a structural component as well as it has got a unstructured component. So in the case of social media, mainly these are unstructured ones. So here the things perform well, but in say news domains or books or other areas, the grammatical sentences are still there, and people use them. So this DiscoCat model is encodes linguistic structure into quantum circuit, puts symbolic AI back on stage, and provides algorithms that no longer act like black boxes as neural networks basically do. So the explainability of the interpretability issues is people now are more concerned, instead of looking at the neural models as the black boxes. So the symbolic AI basically again has become important. And the syntactic structure, one example, like say the way we used to learn, that is the grammar procedure, that is the procedure basically. So that's the bracket structure, and some way of writing is like, say, for example, the word arrow means that and the -1 on the left side means that if along with arrow, if there is a determiner at the left, so the whole thing becomes to remain the atomic type is noun. Similarly, the case it is for the light, that is, it is an adverb, and noun appears on the right side, the whole thing remains as an adverb. That is basically those are the main concepts. Noun says that kind of way. This is the way the writing has been done. That is in the DiscoCat model. Basically, to again look for that is how it can be implemented in quantum algorithm. An example of parsing in a DiscoCat framework, that is, these are the basic units and sign and arrow.
So, and there is a histocat structure, and finally we can see that that is for the sentence like time flies like an arrow, and basically time is a noun, flies, that is, it is a transitive verb, so there has to be a noun on the left side and an adverb on the right side, and again the rest of the thing you can see there, and finally by decomposition we actually, by the composition principle, we arrive at the sentence model. So the parsing becomes complete. So that is the way the histocat model basically represents the sentence. It is a traditional way of writing the production rules basically. That is only a formalism that they have considered is to see that they can be represented in the quantum model. Now why we are looking for the sentence, trying to give a structure to the sentence in this way? It is because of the long-term, long-distance dependencies that are present in a sentence. That is one part of the sentence is interested, is linked to another part at the end. And in between there can be a large number of words basically. So bag of words or the name-based implementation, they have a limiting context given to a length, and the recurrent neural networks that we use, they offer the possibility to increase this length by orders of magnitude, and especially when the attention mechanism is implemented. And discarding the underlying structure leads to increased uninterpretability of the algorithm prediction. So what means that is done in the neural model as well, cognitive as well as lexical. Cognitive is basically you refer to the object to which the word basically refers to. And the lexical means with the definition, the grammatical category, synonyms, antonyms, then gender, number, etc. And in NLP, we use the distributional hypothesis. That is, a word is known by the context that it fits. That is, words with a similar meaning, they appear with similar context. That is the concept of the what to get model that is generally used for this one. Now, when you look into the sentence structure, it is basically the tensor product representation to capture the syntactic binding. The idea is that, okay, for every word we have the word to bake or the word embedding point. And the idea in the TPR or the tensor product representation by is basically that every word can be attached to every other word in the sentence. So that by that concept, basically the long-term dependencies in the sentence are supposed to be taken care of. So the authors, Aix, Sabrazadeh and Clark, they developed the CSC algorithm, which develops an implementation of tensor-based representation of the meaning of a sentence. And this algorithm can be implemented on a quantum computer. That is what a histocat model is basically all about. Now, some steps of the histocat model is basically that one is a tensor product representation. Every word, that is the sequence of words in the sentence. So there is a tensor product calculation among them. And then you have this linear map of the from the sentence. You have the corresponding histocat model. So finally, we can identify that this sentence representation on a classical machine, the complexity of calculating the full tensor product is basically that increases exponentially. So as sentences increase in length, the CSC algorithm computational cost grows at an exponential rate. And for example, say for the sentence a very light word, and so generally the word meaning is represented as the context in which it appears. So let us say there is a basic size of 2000. That means what the meaning of a word is represented by 2000 words which are actually appear closer to the word in a very large corpus. So that is the basic size, and there are say 2 individual words, maybe lights and words, and for each of them there are 2000 bits are necessary, because 2000 words actually, so each of them can be represented by a bit position. So, and there are 3 words, so it is 2000 to the power 3 bits, that is in a classical machine. If the sentence very light words have to be stored, and the requirement will be 8 into 10 to the power 9 bits basically. In a quantum, because say the way implicit encoding we have seen, it is log base 2 to the total requirement in the classical model, because it comes down to the logarithmic scale. So log 2, and it is a log of the 2000 to the power 3, so 32 bits basically. And if we consider say 10,000 sentences, the classical model requires 8 into 10 to the power 13 bits, and the number of Q bits only increases to 47. So this is basically one of the biggest advantages of using the quantum compute. And again, just to have an idea, that is how these benefits are appearing. It is that every word is represented in a neural model, in the word-to-vec model, because the meaning of a word is represented by the context in which it appears. And in this case, we have assumed that there is a context of 2000 words. These words are fixed, and for some of the words, say for example, say meaning, or say light, or say what, some of these 2000 words will be present in the context, but some of them will not be present in the context. So they can be, these words positions can be either 0 or 1. Either that word is present in the context or it is not present in the context. So by that, for every word, say we will calculate that it will require 2000 bits. And there are 3 such words, so the total requirement will be 2000 to the power 3, and that is 8 into 10 to the power 9. In a quantum computing hardware, the requirement will be log base 2 if you go for amplitude encoding, for example. And so this is and this becomes an advantage. And here you can say the concept of basically the superposition that has come into place at this point. So quantum algorithms for NLP tasks, like say the classification task. So people are working on word embedding, sequential models. Yeah, and for quantum classifier for NLP tasks, this is actually the taken from what Partho and this team was doing there. So only some, so maybe he will be touching that point. So only thing that I want to point is that, or you can see that is in some cases, the theoretical algorithms are very good in performance, but they require a quantum RAM basically. And because quantum RAMs are, there is no such quantum RAMs as of now. So because of the lack of quantum RAM to execute, the algorithms cannot run on the current quantum machine. There is a quantum.
Long live India and France friendship.